Hello and welcome back to Calculus 1, section 5.2 on definite integral. So what's going on now? We have our approximation. Left or right rectangles or mid, pick your poison, right? It's approximation, it's not exact. So what do we say? How do we get better? By placing more rectangles. So now we add more rectangles to the mix. That reduces error. Then we add even more. Then we add even more. After this, carefully add even more. It gets busy, right? We are still on A to B to get our delta x to be B minus A over N, number of rectangles, right? But the trick is that if you go and send n to infinity, you can see that you will have infinitely many rectangles, and because this is now infinity, each one of those rectangles is infinitely thin. Infinitely thin rectangles fit under each point of the function, having zero error. And they produce what? Exact area. How do we mathematically construct that from a single rectangle? We said that the single rectangle, now we're changing notation a little bit, but single rectangle was, and we'll use CI instead of f of x. F of xi, we use f of ci. So this is going to be the height times delta x. So this is one area, right? One area. Single rectangle. What do I do next? I add rectangles from 1 to n. Now this is many added together. And then finally I send that n to infinity. This is infinitely many equal exact. So obviously if you use only one rectangle, the result is going to be abysmally bad, right? You're going to have the most amount of error you can possibly think of if you use one rectangle. But then in the previous section we said let's use 4 rectangles, or let's use 5, or let's use 8, whatever. 10,000, right? We mentioned. Whatever you want to use, right, and add them all together because of the sum, you will have many rectangles which will give you a good approximation, right? So now all I need to do is to send that finite amount of rectangles to infinity and produce exact area in our calculation. Because, again, your n, number of rectangles, goes to infinity and your width goes to 0. Because you're dividing a finite number, let's say 7 minus 2 is 5, by infinity. That goes to 0, right? So the rectangles are infinitely thin, and they are stretching exactly up to the function without any error because they are infinitely thin, they fit into a single point, right? So there is no room for error. It stretches exactly up to how far it has to go. So infinitely thin, infinitely many of them, when we add them all up, they add to exact area. So this formula will produce exact area. So exact area is given by the limit n goes to infinity, summation I goes from 1 to n of f of ci times delta x. So this is exact area. Find the area under f of x equals 2x squared plus 4 on 2 to 6. So find the exact area in this place. So what do? We have to set up everything first before we can actually compute any of these things. And there's a lot of setup. So we start by first figuring out, let's first draw arbitrary thing like that and say this is what 2 is, this is what 6 is, and we have these divisions in between. We understand that at 2 was x0 and the next one is x1 and x2 and x3. We can calculate delta x right away as 6 minus 2 over n, because we are going to use infinitely many n, so just leave it. And we get 4 over n. So that is our delta x. The next order of business for us is to deal with this ci. You see, ci is the x value that goes from one location to the next, to the next, to the next. And if you take a look at this partition, you are starting at A, which is x0. The next one is x1, and the next one is x2, and the next one is x3, and the next one is x4. You have delta x every time when you make a jump to the next one. So how do you go and express each one of these in terms of the ci? Well, you're starting at A plus I times delta x. That's a formula for it. Think about it. You start at A, you add one delta x, you are at x1. You add another one, you are at x2, x3, x4. 1, 2, 3, 4. 4 times delta x, right? To get from the A to x4. So we can track location by using this formula. So now I can calculate that ci because I know that my A is 2. So ci is 2 plus I times 4 over n. Now, guys, I is a counter. It's not complex root negative 1. I is a counter that we use. Could have used K, could have used L, could have used any other letter. So this I is a counter on the not complex. I not complex. All right, it's a counter. So now I have to find f of ci. Well, that's easy. I know my f is 2x squared plus 4. So here, 2ci squared plus 4. And I know what ci is. So that's 2 plus 4i over n squared plus 4. And I'll work this algebra. What do I have? I have 2 times. This is square of binomial. So that's 4. 2 times 4 is 8, times 2 is 16, so plus 16i over n plus square, it's a 16i squared over n squared, and we still have plus 4. 2 times 4 is 8, plus 4 is 12, so 12 plus 32i over n plus 32i squared over n squared. Yay! I have my f of ci finally. Ready to plug it in. Exact area is equal to the limit n goes to infinity, summation I starts at 1 goes to n, and now I have f of ci, which is 12 plus 32i over n plus 32i squared over n squared times delta x, which was 4 over n. All we need to do is to compute this limit and we're good. So now distribute. That's the first order of business. So this is going to be limit n goes to infinity, summation I1 to n. And when you distribute, what do we get? We get 48, that parentheses, right? 48 over n plus 32, 120, 128 I over n squared plus 128i squared over n cubed. So now when we distribute, next one is split. We split this, each term gets its own sum. Because you can split addition, right? So limit n goes to infinity. And now in parentheses I have a summation of 48 over n plus summation of 128i over n squared plus summation of 120i squared over n cubed. There we go. Each one of these is I starts at 1 goes to n, right? And now we use formulas. Use formulas, page 345. Says summation of a constant is equal Cn. Summation of I is equal to n plus 1 over 2. Summation of I squared is n plus 1, 2n plus 1 divided by 6. So these are the formulas that are in the book. And as you can see, they operate only on i's. Everything else is a constant. It can be kicked outside. So limit n goes to infinity, open parenthesis, and I kick out 48 over n in front of the summation. I just have 1 inside. Plus kick out 128 over n squared. You have just I inside. Plus kick out 128 over n cubed, and you are left with I squared inside. So you see how the formulas kick in now and take care of all of this? Limit n goes to infinity. The first one is just 48 over n. Times n, right? Because this thing is n. Maybe I should do that in orange. Plus 128 over n squared times n plus 1 over 2. Again, orange. This stuff is that term. Plus, plus 128 n cubed. And now this one becomes the long one, which is n plus 1, 2n plus 1 over 6. Orange, that stuff is there. I'll point also the formulas this way, so it's clear what we are using to do this transformation. I hope you see that we are done, because I don't even need to write limit anymore. We are done. The n and n cancel, and you have your 48. Plus, we only look at the front coefficients over here, because everything else goes to 0, right? Our n goes to infinity. So I have 128 n squared over 2n squared. They will cancel. And then I have 128 times 2n cubed divided by 6n cubed. These guys cancel. So all I have to do is 48 plus 64 plus, this will cancel down to a 3 plus 128 over 3. This is 112, right? 112 over 1 plus 128 over 3 times 3 times 3. 336 plus 128 divided by 3 for a total of, that's a 4 in the back, and then 6 over here, and then 4, 3, and that's it. What was that? 2x squared plus 4, right? From 2 to 6? Got it. Perfect. If you don't believe me, there's the 464. 464 over 3. So, easy, right? No problem. A little bit rough around. This is an amazing conversation starter for 2 days from now. Someone asks you how you, especially if they haven't seen you, you know, because it is, right, the gathering. People won't see you for some time. They say, okay, what have you been up to?
And I started writing sigma on
the napkin,
yeah, exactly.
Right? Especially if they're those nice linen ones.
And I scare them. I'm like, look, it's a big E. It's scary.
That's exactly what you start, right? Or when the evening gets, you know, a little bit further away, someone pulls out, what do you know? Right there. As soon as someone says, what do you know? Go there. Or if anyone brings their kids to complain about how algebra problems are too long. Showing a 2-page problem. And say it's easy, obviously. No, this is not a problem, right? So what was this problem all about? Well, we want to compute the exact area. And now we have a tool to compute exact area, because all of the components of this we can find. We can find delta x using the formula. You can find the CI, which is inside the function, using the formula. Then we can finally compute the function, plug everything in, and this is always the same. It's just a grind. Distribute, split, use the formulas to convert each one of the sums into these expressions, run through some arithmetic, and you have your answer at the end. Looking good. So that's the way to do it. Apparently, if you integrate 2x squared plus 4 from 2 to 6, the answer is 464 over 3. There's that part as well. So now we have a dilemma, right? Like when you go to the doctor's office to get glasses, right? It's going to be 1 or 2. Remember your long definition for derivatives?
Yeah.
And then how everyone loved chapter 3 because... Exactly. So this is one of those situations, right? You have the limit definition for the definite integral, or you can just do the antiderivative and be done in 2 lines. Yeah. Yes, long way.
So, what you just wrote is the answer for that.
Well, I didn't really solve it because I still have to write the formula for this, but yeah.
So that's all we have to do.
I hope you're not disappointed. You can always do the longer way. I mean, it's... I will not try to limit you in any way to express yourself. So, what do we have? Integral of f of x dx calculate between numbers a and b is going to be the antiderivative f of x computed from a to b, which is calculated at f of b minus f of a. This is definite integral. It gives area under the curve. Capital F of x is antiderivative. And you know how to find that one from previous class. So, if I have integral of 2x squared plus 4 dx from 2 to 6, I will integrate this into 2x cubed over 3 plus 4x and compute that from 2 to 6. Now, this will be 2/3 6 cubed plus 4 times 6. This is when I plug in the upper limit because the formula is f of b. You are plugging in the value b, which is 6, into entire antiderivative f. Minus, in parentheses now, you are plugging in 2. So I have 2/3 2 cubed plus 4 times 2. And then you run this arithmetic. Alright, so 6 times 3, I'm going to steal 1 6 and cancel the 3, so that's 36, that's 36 times 4 plus 24 minus 16/3 minus 8. When you distribute the minus, that becomes negative there. 36 times 4, that's 120, 144. Plus 24 minus 8 and then minus 16 over 3 at the end. 24 minus 8 is 16. So this makes 160, right? Minus 16 over 3. Over here we're going to do over 1 and then times 3 and times 3. That's going to be 480 minus 16 over 3 for a total of 464 over 3. how much calculus did we do? Well, right here to do the antiderivative. The rest is arithmetic. All right, the rest is arithmetic. Now, if you don't want to learn this procedure, you can always do this instead, because they do the same thing. And ultimately, the choice is yours. Why would I? Unless you want to. That's.
No, because
Yeah, but still, that's 5 minutes. Wait, are you asking for a special exam?
no.
Just check.
Give me the green test.
The green test, exactly. Good. So, area under the curve. We'll do more examples, obviously, next class. I just want to cover, let's say, one more. Let's say your triangle over here is 3 tall. It stretches 1, 2, 3, 4, 5 this way. And we are asking for the area. Well, we all know what the area of the triangle is. 1/2 base times height, right? Which is 1/2 times 5 times 3, which is 15 halves, right? 7.5. Done. Now, why simple if we can complicate things, obviously? So we're going to use the integral here. So what is the integral going to do? Well, integral is going to take this function f of x and run it from 0 to 5, because that's a and b. So you can think of this representative rectangle delta x, which swipes all the way from 0 to each one. There are infinitely many of these delta x's. So you can think of the first one being lined up at the y-axis, and then the last one here colliding with the dot at the end. So area is going to be given by the integral from 0 to 5. And now I need a function here, dx. Now what's the function? Well, it's the linear line, right? And the linear line has what? Slope m, which is 3 up and 5 over, and it's negative. And it has y-intercept at 3. So, negative 3/5 x plus 3. Very simple. That's our function. So we now integrate this. This will be negative 3/5 is a constant, and then x squared over 2 plus 3x from 0 to 5. So this is going to be negative 3 over 10 times 5 squared plus 3 times 5, right, because 3 times x, minus big fat 0, because when you plug in 0 into x squared and plug in 0 there, it's just going to be 0 everywhere. I'm going to steal one of the 5s and cancel with 10. So I have negative 15 over 2 plus 15, which is 15 over 2. It's also come in handy if you are tutoring, 5th grader or something, and you tell them the area of the triangle. They say y. There you go. Right. You can explain the rest of the stuff that you need to build up along the way. It's called just-in-time teaching. So we'll stop here, and then we'll pick up on Tuesday. Bye.